This lecture will be about flow sensors. So we'll see that we'll be able to measure with different principles, and we'll see some industrial examples. Now let's first define two types of flow. Some instruments that you will see today will measure volume flow, and some instruments will measure mass flow. So directly mass flow or directly volume flow. The volume flow is a given amount of material that will pass through some given cross-section at some unit of time. So the volume flow has units, for example, in cube meters per second. I will use the symbol QV. The mass flow is the flow of mass, so how many kilograms flow through some given cross-section in the unit of time. So for example here, kilograms per second, and I will use the symbol QM. So this is the definition of flow. So if I use any of those definitions, I can use this as a calibration instrument. Again, some of the other industrial instruments may not use directly this definition, but they will measure the speed of the flow and they will multiply it by the known cross-section. Actually, this will be the case of 3 out of 4 principles that you will see today. So then it's still simple. We measure somehow the speed of the flow. We multiply it by the cross-section and we have volume flow. And if we multiply that by density, we have mass flow. So some of the principles that you will see will measure this, will measure speed, and only the last one, the Coriolis, will measure directly the mass flow that we will see today. So what principles can we use to measure flow? Now there are many principles used in industrial systems. I will show you only 4 of them, only the most common ones that you may find in industrial applications. We will take a look first on the differential pressure sensor, and out of those options we will actually see just the orifice plate. Then we'll take a look on the ultrasonic, electromagnetic, and then in the end we'll discuss the Coriolis flowmeter. Now those 3, the first 3, they measure the speed of the flow under some given assumptions, and the Coriolis flowmeter will measure directly the mass flow. So let's start with the orifice plate. Now this is called the differential pressure sensor. So we'll see that we will use a differential pressure sensor as we've seen like 10 minutes ago. But in this case, we will calculate what is the flow rate. And therefore we need to create some pressure drop on some element. And this pressure drop will be created on an element that's called an orifice plate. So this is the orifice plate. It's nothing else than a piece of typically stainless steel, like a circle with this shape, that you mount inside of a flange, and you use this inside of the pipe. So this is the pipe where you actually want to measure the pressure and flow, and here we create an artificial restriction. So here we have a diameter D, here we have the small diameter in the orifice plate. Now the ratio between D and D is given by standards. It's given in tables. And what will happen? Here we originally had some speed V1. So this is the flow in the pipe that I want to get. And now if I take this speed times basically the cross section, I could get the flow rate. And that's the point of this flow sensor. What will happen in this artificial restriction is that the mass cannot disappear anywhere. So here this speed has to be higher. in order to pass through this smaller opening. And therefore we will be able to see a pressure drop. So this is a larger speed, and here we will have a smaller pressure. So we need to measure the pressure before and after the orifice plate. So we'll be needing some differential pressure gauge. Now this is how the pressure looks like. If you measure the pressure at the wall, and if you would move the pressure tab somewhere like this, you would see a constant pressure. Now before the orifice plate there would be a slight increase of pressure, and there would be a sharp decrease after the orifice plate. Now the distance between the pressure tab and the orifice plate, that's actually defined in the standards for the orifice plate. So it's not like randomly placed. You need to know how to place it correctly at what distance, for example. However, here we see that there is a pressure drop, and this pressure drop will tell us what is the actual flow rate in the orifice plate if we calculate it properly. Here, after the orifice plate, now we'll have a small permanent pressure loss. So the pressure after the orifice plate will be always a little bit smaller than the pressure before the orifice plate. Now I recommend you to take a look on this video and on the other videos in this lecture as well, because they are quite interesting. You will see how this is installed, and also the explanation again of all those principles. Let's now take a look on the pressure drop P and how can we calculate the actual flow. Those equations are derived from fluid mechanics, so they are based on the Bernoulli equation. Here we have the cross sections of the orifice plate. So A1 is the cross section here in the pipe, and A2 is the cross section in the orifice plate. Now it's clear that no material will be created or disappear in this orifice plate. So the flow rate that we have here in the pipe and in the orifice plate has to be the same. This is this equation. And we want to calculate what is the speed. So we use the Bernoulli equation, and we correlate the speed difference here to the pressure difference. So this is the delta P that we are looking for. So at the end, the equation looks like this. Flow equals to something, and here is the delta P that we actually measure. Now note that everything else is a constant value. Alpha and epsilon are coefficients that describe the liquid, and alpha is a coefficient that describes the properties of the orifice plate. Here we have the diameter, so this is again a constant value, and the rho is the density, so this may change if you have a changes of temperature. So we take a pressure gauge, we measure a differential pressure, and we calculate this flow. Now note that this is a square root dependence, so this isn't not typically but linearized with some electronic circuit. The basic dependence is non-linear. We can see it here. It's a square root dependence. This is how the orifice plate looks like. So here we have the orifice plate itself. Now typically here there is a hole that allows sediments to pass through the orifice plate, so that they don't need to go through this main opening. Here we have the downstream pressure tab, and here is the upstream pressure tab. This distance is defined by the standards, and the diameter is defined as well. Now what can we expect and how does it look like? This is the orifice plate itself. This is the orifice plate mounted in an industrial application. So the orifice plate is here. Here we've seen that like 20 minutes ago. This is the differential pressure sensor. This is the valve, and this is the valve that allows you to disconnect all the system. And again, this is an example of the orifice plate. So with a flange like this, you can disassemble those screws and you can replace the orifice plate. It's very sensitive to mechanical damage, so you need to have a precise shape here, precise angles here so that it measures correctly. And it's not suitable for applications with abrasive materials, for example. Let's take a look on the installation. Now, the major disadvantage of the orifice plate is that it needs a very large distance before the orifice plate. So if you look on this picture, you can see this symbol. It's telling me that the flow rate needs to go from the left to the right. It cannot go from right to the left. And this is a very large distance. And this is typical for an orifice plate. And actually this distance depends on where you install it. And it depends also on the parameters of the orifice plate. Now, the parameter of the orifice plate is the diameter of the orifice compared to the diameter of the pipe. And here in this table they call it beta. Here we see typical values, so something like 0.7. So if, for example, let's say this would be 10 centimeters, then this would be 7 centimeters, the diameter of the orifice plate. And the distances that you see here in the table, they give you the distance before the orifice plate in multiples of pipe diameter. And the letters stand for different configurations. So for example, case A, you can see that here we have the orifice plate. Here there is a fully opened full-way valve before it. And the minimal distance that you need to keep between the orifice plate and this valve A, in this case, is about 20. So imagine that here, for example, you may have like, let's say 10-20 centimeters diameter of the pipe, and you need to have this straight section at least 20 times available. So this is the biggest disadvantage of the orifice plate. After the orifice plate, it's typically 5 pipe diameters. So here it's not as long, but the length before the orifice plate is typically very large. And now note that this gets even bigger and bigger. For example, if we have this configuration where we have the case C, this is this case, we have the orifice plate here, and we have two bands at right angles. So the pipe goes like this, and then it goes in the front and then goes to the bottom. And in this case, the minimal distance between the orifice plate, so the minimal distance of this straight section, is 63 times the pipe diameter. So it may not be even possible to install the orifice plate sensor in your application because you simply will not have this straight section available. Again, after it's typically 5 pipe diameters, so all those cases here are showing 5. Last example, for example, case F here, just one right angle band. Here the minimal distance is 29 times pipe diameter. You can see that this varies also with the ratio here, and if we have a different ratio, it may be smaller or it may be bigger. So the biggest problem of the orifice plates is actually to find the installation place where you have a straight section that is long enough. Here is an installation example. So here is the orifice plate. Here you can see the valves that allow you to disconnect all the systems. So this valve is either fully closed or fully opened. Here we have the differential pressure gauge. We may have temperature sensor as well for the compensating of temperature changes. Here this is called the flow computer, and it takes in the differential pressure, density, and eventual ambient pressure, and based on the equation that we've seen, it can calculate the actual flow rate. Now let's take a look on the advantages of orifice plate. Now it can be used for liquid, gases and steam. It can be used for very high pressures, so several megapascals, not a problem. It can be used for high temperatures, about 1000 centigrades. It can be changed without interrupting the process. Here I'm talking not about the orifice plate itself, but about the actual instruments. So if you want to change the orifice plate here, okay, you need to interrupt the process, or you need to have some bypass like this so that you can temporarily close all this. But you can close those walls and you can change this pressure gauge, you can change the temperature sensor and so on. It can be used for wide pipe diameters. The standard actually starts from 50 millimeters and above. So based on the standard, you can select a ready-made orifice plate. In the general group of restriction type devices, which the orifice plate is just one of them, it can be used typically from about 10 millimeters to about 5 meters. If you use a pitot tube, for example, in an open channel, it is typically something like up to 12 meters. So it can be used to measure very large flow rates with very high temperatures and very high pressures. Now what are the disadvantages? Now one disadvantage is that it has a limited turn down ratio. Now this means what is the minimal and what is the maximum flow that I can actually measure. And for the orifice plate it's about 5 to 1. So it means that I cannot measure the very small flow, and I cannot measure very large flow at the same time. So there is a given ratio between the minimal and maximum flow rate that I can actually measure with this. And as we will go through the other principles, we will see that the turn-down ratio will improve more and more. Now, the edge of the orifice plate can erode over time. So if you have a liquid or some mixture of liquid and solids that can actually damage the orifice plate, then the orifice plate is not a good choice. You need to maintain it, you need to maintain the angles on the orifice plate, and if this gets damaged, you lose the accuracy of the sensor. And the biggest disadvantage is that you require a very large upstream and downstream distance. Some more disadvantages. It's not suitable for very small flows. It's visible from the equation. If you have a small flow rate, then you will have a very small pressure difference and it will be difficult or impossible to measure. It does not work with very viscous liquids. So if, for example, if you would like to measure honey, then it's not a good idea to use an orifice plate. And it cannot measure directly density, viscosity and concentration. Now this will be the case of the flowmeter, which will be the Coriolis flowmeter. And I've already said that this is not suitable for abrasive liquids. So if you have a mixture of water and sand, then it's not a good idea to measure this with an orifice plate. Okay, let's take a look on the second principle for flow meters. And we'll be talking about ultrasonic flow meters. Now, this works only for liquids. In industrial systems, I've seen some applications of this also for gases, but it's not that common as for liquids. Now, how is this working? Now, this is the pipe where we measure the flow rate. Here we have a piezoelectric transducer. Here there is one, and here there's a second one. And this transducer can send an ultrasonic impulse and can receive it. So I can send an ultrasonic signal like this into the liquid and to the second transducer, which now will act as a receiver. So I will send the signal from this one like this, like that. Here on this pipe wall it will get reflected. The second step is that I use this as a transmitter. I send a signal that goes into the pipe and back and gets received by this. Now it's a receiver. Now if there is no flow, then the time it will take for the ultrasonic signal to propagate will be the same. So the signal time will be same in this direction than in this direction. Now if there is a flow from left to the right, now the actual time from this one like this to will be shorter than in the other direction. Now if it goes upstream like this, it will be carried together with the liquid, and it will be shorter. So we are actually looking for the time difference. So we first send a signal from, let's call this 1 to 2. So we send from 1 to 2 this distance, and we measure the time. And then we send from 2 to 1 and we measure the time again. And this is how it looks like. You send some ultrasonic pulses, you time it, in flow direction it's shorter, and against flow direction it's longer. And now based on this time difference, it's possible to calculate from the known speed of sound what is the flow velocity. And if you know the velocity here, you multiply that by the cross section and you have the flow rate. Again, I recommend you to take a look on this video. This is just the principle, but you may equip this with multiple sensors if you want to measure the flow profile. The flow profile actually, well, if it's just with one pair of sensors, it would look like this. So this would be the flow profile, but from fluid mechanics we know that it's not like that, and it's typically something like this. So you can of course use multiple transmitters to measure the flow profile with higher accuracy, and that's actually what they explain here in this video. This is how it looks like. So this is the piezoelectric transducer. I see it's some problem with the fonts on my computer. Anyway, this is the piezoelectric transducer. Here this generates the ultrasonic signal. Now through this wedge it gets transferred into the wall, and from the wall into the liquid like that. Here on the second wall it gets reflected, and it is received by this second transducer. Now this is the electronic circuit, and this is the electronic circuit that is used by the transmitter and by the receiver. And if we now have the info about the flow rate, V, the flow velocity, we will multiply that by the known cross section, and this will be our flow rate. So this is not based on the definition of flow, but this uses the velocity profile. What are the conditions when this is working? Well, of course, we need to prevent any absorption of the ultrasonic signal. So the limitations are that the volume of gases in a liquid needs to be smaller than approximately 2% by volume. The reason for this is that in the gas, in the liquid, we have different sound velocity than in the gas. And since we don't know what is the amount of gases that we have in the liquid, we cannot compensate it for this by calculation. If we are talking about solids, again there is a limitation, typically something like 5% by volume, and this is due to the attenuation of the ultrasonic signal on the particles. Installation should be done as follows. do not install that from the top, because here you may have bubbles, and do not install it from the bottom, because here you may have sediments. So the correct installation is from the sides, left and right, so that the signal is going like this, and eventual bubbles, they will be up, and eventual sediments will be down. Also, we need to avoid partially full pipes. The reason is simple. If we measure the speed profile in here, we are multiplying this by the normal cross section, and if the pipe is not full, then we will not be able to calculate the correct flow rate. This is the explanation about the particles in the liquid. So here we have the liquid, and if you have some particles, now this ultrasonic signal will be attenuated on the particles, and you will not receive enough reflection on the wall here that you are actually looking for. So it's difficult to receive a clear echo. So an ultrasonic sensor for flow is not suitable for mixtures of water and sand, for example, where you might have these problems. One of the biggest advantages of the ultrasonic flow meters is that it can be mounted from the outside on the pipe, and you don't need to interrupt the process at all. So this is called a clamp-on system. This is the pipe, and you mount one transducer from one side and a second transducer from the other side, and it goes through the wall. Here you apply special grease so that we have a good contact for the ultrasound between the sensor and between the pipe, but the process is not interrupted at all, so you don't need to stop your production, you don't need to care about the aggressivity of the liquid, and you can measure directly in the pipe. What can you expect? It can measure clean liquids and gases. The accuracy is typically about 2% when you install it correctly. If you calibrate it properly in the reference conditions, it may be something like 0.5%. Now the clamp-on system can be used typically for pipes up to 5 meters, and the inline system, that's the actual sensor, we'll see in a minute some examples, that's mounted in the pipe, that's typically up to 2 meters. The temperature where this works, the maximum temperature is much smaller than for the Orifice plate. Here you see some data about from this manufacturer. They are claiming something about 170 centigrades, so it's much smaller than the Orifice plate. Advantages. And the turndown ratio is about 50:1 for liquids. So if you compare this to the Orifice plate, there we had 5:1 approximately. So here the ratio between minimum and maximum flow rate is actually 10 times larger. For the clamp-on design, we do not have any pressure loss at all, and we don't have any abrasion or corrosion from the fluid, because that's where it's separated by the wall of the pipe. Now the Orifice plate was used only for one direction, but the ultrasonic can measure in both directions, so the flow may go from left to the right, from right to the left, and no problems. This is the before last point. That's for the clamp-on system. It can be measured without interrupting the process, and if you have the clamp-on system, the price is virtually independent on pipe diameter. You still have the same sensor, you just have a different fixture where you fix it on the wall. Now disadvantages. It's not suitable for small flow rates. It's not very suitable for viscous liquids, so for example honey. It cannot measure steam because ultrasound will not propagate in steam, well, not in the way that we can detect that. And it cannot be used for suspensions. So if you have a mixture of a liquid and a gas, or liquid and solids, then it will not work. It does not have a traceable calibration. This applies for the clamp-on system because the mounting will change, and if you want to have traceable calibration, then you need to have the inline system. Here are some examples. Again, for some reason the text is not visible, but at least we can see the pictures. Both are the clamp-on system. So this is the transducer. So you mount this on a pipe. I have the picture a little bit later. And then those units are connected to this instrument where you actually have the signal generator and the electronic circuits that provide you some output. This is how it looks like. So this is the clamp-on system. Here we can see an installation example. So the transducer like this, the signal goes through the wall like that and back, and it measures the flow velocity times cross-section gives you the flow rate. You can see how simple the installation is. We can see approximately the temperature ranges for this particular type of sensor, so about 80 centigrades. And we can see about the diameters where this is working, so from about 15 millimeters to about 4 meters. And in this picture you can see the inline installation. So this is a flange like this, an armature, and you need to interrupt your pipe like this with a flange, and you mount it in there, and here you can actually see that this is the version where we have the two ultrasonic transducers on each side. So there are two here and two from the back side. So we measure the speed profile more accurately in the pipe cross section. This in turn has a traceable factory calibration because we can calibrate that under known conditions. So typically this is more accurate. Now, this is very common in industrial systems, in water treatment industry, chemical industry, and so on. So based on the type of liquid that you actually have, you can select different materials in the transducer. How to install it correctly? Well, it's a little bit better compared to the Orifice plate. It still requires some downflow, some upstream and downstream distance, but this is smaller. Now if we have a band before the sensor, now this is about 5 pipe diameters, and after we again have 5 like this. So in all sensors we have 5 pipe diameters except the last configuration here. If we have a pump, now this is 15 and this is 5. Now if we have a valve, then it is something like 10. If it's a fully open valve, then this is something like 5 times only. So we can see that the distance gets smaller and smaller. Now this is a valve as well, but this valve is used to control the actual flow, so it distorts more the flow profile. So in this case we need a larger distance. Okay, that's the second type. Now we still have 2 more to go. The electromagnetic flowmeter. Now the electromagnetic flowmeter has one difference compared to all the other ones, and the difference is that this works only for conductive liquids. So your liquid needs to have some electrical conductivity. here we can see how this works. This coil will create us a magnetic field. So we'll have a magnetic flux density oriented in this direction. The liquid is conductive, so it's flowing like this with some velocity v. And since it is conductive, it is acting like an electrical conductor that is moving in a magnetic field. And therefore will have some induced voltage. And the induced voltage will be oriented perpendicularly to the magnetic flux and to the velocity. So here in this direction we will place two electrodes so that we can actually sense this induced voltage. Now this induced voltage will be connected to an amplifier, and this voltage will be quite small. But if we amplify it, then we may find the function between the flow rate and between the induced voltage. Finally, when we have this flow velocity, we simply multiply this by the known cross-section. So here again, this distorted equation should be Q equals to some V times the cross-section A. Again, take a look on those videos, they are quite interesting. Now this is just the principle. In reality, you need to compensate at least for external magnetic fields. So the way it's done is that we change the current direction in this coil. So if we have a current that goes in one direction, we'll have a magnetic flux density going also in one direction. So this is DC current, and let's say it starts like this. Somewhere here we have the constant current. When we then reverse the polarity of the magnetic field, we'll get this reaction, and actually those colored rectangles are the sampling intervals. So we sample multiple samples here, we sample multiple samples here, and we are trying to reject the eventual noise that we may see here, for example. So it's not a permanent magnetic field that could be created by a permanent magnet, but it's a variable magnetic field. So we maintain one polarity, one amplitude, we measure, we then switch the polarity, we measure again, and this will compensate the external magnetic fields because they will act like a DC component that we have in the measured data. This is how it looks like. Here this is the electrode, one here and one there, and here this is the coil that actually creates the magnetic field. Let's take a look on this picture. Here we may see it a little bit better. So now here we see this is one electrode that measures the voltage, and the second electrode will be from the back side, somewhere here. And actually this is a pole that distributes the magnetic field. So here, here, and here there will be the coil that creates the magnetic field, and then this is evenly distributed in the flow meter. So it would look something like this. This is the pipe. Here we would have the pole. Here we would have the pole on the second side. This would be the magnetic field like this, and from this side we have one electrode, and from the other side we have an electrode like that. Let's take a look on some examples. Here we have an example from the food industry. The temperature range approximately, this is typically limited by the material of the liner that we have, because the liquid needs to be insulated from the walls. So here this is a non-conductive piece. So here this is not the pipe directly, the metallic pipe, but there is a lining material. And here we can see different materials like PFA, Teflon, and so on. Many industries use this flowmeter type, so chemical and processing industries, water and wastewater treatment, and so on. You can see the different materials like polyurethane, rubber, we can see Teflon, and so on. They have different properties for different temperatures. Here you actually may see the liner. Here it is this black stuff, that's the lining material, so that's the insulation, and this is the pipe, and here we can see that this is creating the magnetic field in the system. What can we expect? It's working only for conductive liquids where the conductivity is above approximately 1 microsiemens per centimeter. So if your liquid is not conductive, you cannot use this type of flow meter. Now the accuracy is about 0.5%, and if it's calibrated, if you have a very accurate instrument, it may be something like 0.2%, so it's very accurate. It's working for pipe diameters of about 2.5 meters, pressures about 4 megapascals, and temperatures about 180 centigrades. So it's approximately the same temperature range as the ultrasonic flow meter. It's definitely much smaller temperature range compared to the Orifice plate. In terms of turn-down ratio, it is however much better. So here we can expect the turn-down ratio of about 1000 to 1. So for the ultrasonic we have about 50 to 1. For the Orifice plate we have about 5 to 1. So here it is, let's say, 200 times better in terms of the turn-down ratio compared to the Orifice plate. Now there is no pressure loss, or very small pressure loss, and it can measure also highly abrasive liquids. So for example, sand, water mixtures, or slurries, and so on. So here it's not sensitive for those effects, for abrasion, for bubbles, and so on. Disadvantages: it does not work for non-conductive liquids. So if you have something like an oil that's not conductive, then you cannot measure this with this flow meter. You can have problems with sediments because they will simply change the cross-section that you measure. It's not working with cryogenic fluids because they are not conductive. It's not working for gases and steams. Again, they are not conductive. And it's working only for completely filled pipes because we measure the velocity profile times cross-section. How to install it? So first of all, it needs to be full at all times. So the pipe needs to be maintained full. So this is not correct. Here we can see that we have the electrodes here, but here we don't have the completely full pipe. So the best way how not to do it is to install that actually in this type of application. So like this, we make sure that it's full at all times. So if you have a straight pipe, a horizontal pipe like this, and it might not be full at all times, you bend the pipe downwards, you install the flow meter under the axis of the pipe so that it remains full at all times, and here you install a valve to allow you to remove the sediments that may be there eventually. You can see this installation here. This pipe like that, horizontal pipe interrupted, bent downwards, and this is the electromagnetic flow meter, and this is the valve that allows you to drain the impurities. Now the distance in this direction, so upstream, you have 2 pipe diameters. Now here you have 5 pipe diameters. So you see that this gets smaller and smaller. How not to install it? Do not install it like that or like that. So here you can see that this might be full with bubbles, and in this installation, when it's facing downwards, you again cannot be sure that you have a pipe that is full at all times. So this is not the way it should be installed. This is the way it should be installed. Okay, so the ideal position for this type of flow meter is in a vertical pipe where it's going upwards. So here we have the flow meter, we have the pipe like this. Eventual bubbles will go through and will accumulate here, or will continue in the pipe, so they will not stop in the flow meter. It also avoids cavitation. It ensures that you have enough pressure here, and it ensures that it stays full at all times. Okay, and the last flow meter will be the Coriolis flow meter. Now the Coriolis flow meter is based on the Coriolis force. And the Coriolis force is a force that is created on a moving object, and on the object where you try to change its direction. So it works like this. Here we have the flow direction, so this will be the flow meter itself, the input and output ports. And inside we have a pipe that has this shape like this. So you can directly see, if you see an industrial application, then this is a Coriolis flow meter, because you will see a shape like this, but later see some examples. And this tube is where the liquid is flowing, and we will create some oscillating motion of this tube. This is shown here. So here we have a driving coil, and this makes the pipe move up and down. The motion is very small, but we can measure it. So this pipe moves up and down. Now if we have no flow, then the pipe will move like this. You can see now that there is a uniform motion on both sides. The pipe is moving in the same way. Now in this case, this is an example of a system with 2 pipes, but it's working also with just 1 pipe. Now if we have the flow, now this will happen. At one side of the pipe, the Coriolis flow will act in one direction, and here on the other side it will act in the other direction. So here is how it is working on one pipe. We apply the motion, so we make this vibrate back and forth into the picture and out from the picture. So we apply some angular velocity, omega, here. Now we are looking for the velocity of the flow here, so we're looking for this v. The particles that are moving in this flow, they want to stay in this uniform motion, so they want to move like this. And we are forcing them to move around this bending. So therefore they will create us a force here, and in this side the force will go in this direction. Now here the liquid is already moving, and here we are trying to force it back to a straight section, but it wants to stay in this motion. So again, here there will be a force, and this force will be in the opposite direction. Now we can measure the effects of this force. This is this motion that we can see on this animation. and we can actually use this to calculate the mass flow. So if we measure this force by simply measuring the position difference between the left and right sections here, we can calculate what is the mass flow. So the way it works is that here this driving coil makes the pipe move, and here with those displacement sensors or pickup coils we measure what is the actual position. And if there is no flow, then this and this point will move in the same way, so the phase shift will be the same. But if we change the flow rate, then we will have a different position at this instant, at this position, and at the same time here with this section. We can see that here in this animation. Again, I recommend you to take a look on those videos to see actually the instrument inside, and also see some industrial applications. This is how it looks like. Here we see the pipe. This is the shape that is typical for the Coriolis flowmeter. Here this is the driving coil, so this makes the pipe move back and forth like this, and this is the pickup sensor, the position sensor, that actually measures the distance between the pipe and the frame, so it's moving like that. And this unit then is the computer that calculates the flow rate. Now the Coriolis flowmeter can be made either from one pipe or from two pipes. Actually the two type version can compensate for external motions, whereas the one pipe cannot. Inside it looks like this. So here we can see the stainless steel pipe like that, two pipes. Here we can see the different sensors, so it may be a temperature sensor. Somewhere here there will be the driving coil. Here you can see a part of the electronic circuit in the driving coil, so there will be the driving coil somewhere here, and somewhere here there will be the actual position sensors. So this two pipe version will compensate for external motions, and can help you in applications where we have vibrations, for example. Typically this is a stainless steel tube. It needs to be bent for higher temperatures, so typically for above 100 centigrades. The tubes for higher temperatures are typically straight or just have a smaller bending, and they are made from titanium. The Coriolis flowmeter can measure not only flow, but it can measure also density independently. So this is how it works. So here we have the motion of the tubes, and we are looking for the resonant frequency. The resonant frequency is given by this equation here. Now this is the mass of the tube, and this is the mass of the fluid. And if we want to measure the density, we can simply get the volume of the fluid that is known, and by looking for the resonance frequency we can calculate what is the density. So the Coriolis flowmeter gives you an independent measurement of mass flow and of density. This is the comparison of the dual and single tube version. I've already explained that. The dual has a little bit higher pressure loss, but it's not sensitive to external vibrations. Here we have the sensitivity to vibrations, but we have a little bit smaller pressure loss. What are the advantages? Now it can measure directly the mass flow and temperature. Typically there is a PT1000 sensor, and it can measure directly the density. It can also calculate you other properties like concentration, volume flow. If you have a known liquid, then for example concentration of sugar in water, alcohol in water, and so on, as long as the mixture is single phase. So it means you have just two liquids, for example. And it can calculate your viscosity. It is a very accurate instrument, typically about 0.1%, so it's more accurate than the ultrasonic and electromagnetic flow meter. On the other hand, it's also more expensive. It is possible to use it for small flow rates. It's working for cryogenic fluids. The typical pipe diameter is from somewhere like 1 millimeter, which is very small, to about half a meter. And it measures for about the same pressures like the other instruments, so 51 megapascals for this particular manufacturer. Temperatures are a little bit larger than ultrasound and electromagnetic flow rate, so 350 centigrades roughly. It's still about 1/3 of what can the Orifice plate do. Disadvantages. Well, compared to the ultrasound and electromagnetic flow meters, it has a higher pressure loss. It works the best only for single phase liquids, fluids. It does not perform very well if you have two phase fluids. So for example, if you have a mixture of air and gas, it has a very high impact on accuracy, and it's also very expensive compared to the others. Here are a few examples. You may directly see that this is a Coriolis flowmeter. This is the typical shape. Here is where we have the bent pipes, and this is oscillating like this. You can see the installation like that. I have a slide on the next page. So those are typical examples of flow meters. How to install it? We need to make sure that there are no sediments and no bubbles inside of the flow meter, so it should not be installed like this in the horizontal installation, because here you can have sediments and there's no way you can remove them. In this installation you may have bubbles, and that's again wrong. Therefore, it is recommended to have a vertical orientation where the flow is going from the bottom to the top, so like this. This is not recommended, and this is not recommended. It's the same like we had for the ultrasonic. So if I go back to my picture here, it's directly visible. Then the flow rate needs to go like this, upwards, and here there is a source and the liquid is flowing in this direction like that. In terms of minimal and maximal distance, there is none, so it can be installed directly or very close to the bending or to the valve. We can again see it here. This is the valve where they can close it. This is the valve where I can close it. This is the T-piece, and there is no distance between the meter and the bending. So that's another advantage of the Coriolis flow meter.